All right. Pre-labs. Pre-labs in order should contain the following things: paperwork, multi-sim, and finally, fritzing. Paperwork should be anything you need up to and including maybe a drawing of what your technology implementation is going to be. Multi-sim should simulate and show that your design functions as expected. You should start your paperwork. Let's do it like this, paperwork. With an overview of the problem you're trying to solve. Second, probably some form of truth table. Or later on in the semester, maybe a state table. Three, any K-maps or simplification work. So if you need to do factoring or decomposition. 4, a logic schematic. And 5, an implementation. Schematic. Those are the things I'm looking for. Some evidence of what the hell the problem is you're trying to solve. Even if it's just f of ABC equals something, something, something. Truth table. The truth table has to be there because when you do your multi-sim simulation, you're going to be comparing that truth table to your multi-sim simulation. They have to match. If they don't match, the thing you've designed in steps 4 and 5 doesn't do what you wanted it to do in step 2. So you have to be iterative. You have to go back and say, oh, let's check the truth table. Is the truth table right? Yes, it is. That means something is wrong in 4 or 5. Okay, or maybe I didn't wire it correctly in multi-sim. So that's the paperwork. In multi-sim, really all I need is a page that shows me, hey, here's all my gates doing whatever my gates do. I don't know, something like that. Whatever it is, it's shown hooked up to a word generator. Generating that binary upcount sequence. If you have 5 inputs, it needs to count from 0 to 2 to the 5, minus 1. Over here, I need the logic analyzer tool. Okay, look at all of those. Plus, I need to look at all of the inputs. Because without the inputs, the outputs are useless. You have to look at all of them. So you have this on the screen, and also just open up the box for the logic analyzer that shows me A, B, C, D, and F, and shows it low, high, low, high, low, high, low, high, low, high, and continues on like this for some time, and then finally, goodness gracious. I think I lost one in there somewhere. Okay. Shows me that and whatever the magic output is supposed to be. If it's supposed to be low and then high for there and high, some whatever that is. This one page gives me all the information I need to know if my actual device works as my simulation intends. So you do the paperwork so that you compare your multi-sim back to your paperwork. Check out F compared to the truth table. You're good to go. That's your multi-sim. So now you know that whatever your technology schematic has shown works the way you intend it to. Then you've got to build your fritzing. So let's go through the paperwork section for a second. This is my pre-lab for lab 4. It took me about half an hour with questions being asked by various people to put this together. So, oh, actually, where's... Oh, there it is. Okay. So I built a truth table out based on what it told me. I wrote down at the top, oh, if A is 1 and B is 0, or if B is 1 and C is 1 or D is 1. First thing to know is the order of those parentheses makes a big difference to the circuit that you build. I'm here to tell you that that's the correct order of parentheses. So I built a truth table. Then I started simplifying. I said, okay, these are all my prime implicants in red. Those cells make essential prime implicants. You don't have to do that, but I did it so that you would see it. And I came up with an equation, F equals that. Now, the lab says, ooh, you have to build it in the fewest number of chips. So if you're going to minimize ICs, it's usually a good idea to minimize gate input cost. So start with the sum of products. Tell me what the gate input cost is. Hey, all right, this was our initial circuit that we got from our K-map. A and B bar, BD, BC. It had a gate input cost of 10. What else could you do to reduce gate input cost? There's really only one other thing we talked about that can reduce gate input cost.
Simplification.
Simplification how? What?
Boolean algebra simplification.
Yeah, we do use Boolean algebra. I would have said decomposition or factoring. Okay, those two things. Decomposition isn't quite Boolean algebra. It's just kind of selectively grabbing pieces, so it doesn't quite say enough to say Boolean algebra. But factoring is definitely Boolean algebra. So, all right, can we do it with factoring or decomposition? So now you keep going. You look. A, B bar, or B, factor out the B. That's B ANDed with C or D. Its gate input cost is 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so that's better, right? Less gate input cost is better. Except, what's the other piece of this lab? There's one other additional, two?
Or, I'm sorry, you're supposed to use the least amount of chips.
Use the least amount of chips. So we haven't actually counted, don't go there yet. We haven't counted how many chips we're going to use. What kind of chips can we use? Can we use just anything that I handed to you at the start of the semester? You guys, in theory, have already turned in pre-labs for this. I haven't had time to grade them yet, but you should have read the lab. So what are the restrictions on what chips you can use?
NANDs only.
NANDs only. So does this have any NANDs in it? Does that one have any NANDs in it? No. So these are what we call logical schematics. They're the logic, ands and ors and nots. We need to go and build technology schematics. Okay? Now, building technology schematics gets a little interesting. This one is actually fairly straightforward. If you start putting sets of bubbles, you'll notice that everything is already an inverter. Everything is already useful for a NAND. So if I put a bubble on the output of this AND gate, I know it sounds silly as an engineer to be talking about bubbles. What we're really applying here is graphical De Morgan's law. If you put an inverter here, you have to put an inverter before it gets to any other gates, because otherwise you'd be changing the function. So we know that F double bar is the same as F, or X double bar is the same as X. So by putting sets of multiples of 2 inverters, we cannot change the function, even though we're changing what gates we're using. We're not affecting the output. So the only tough one here was the inverter, but you guys have all done experiment 2. You know how to build a universal inverter, or an inverter out of a universal NAND gate. Tie the 2 inputs together. So our chip count, first off, let's look at our gate input cost. Our gate input cost has gone up. Going back here, our gate input cost was 10. But because we can't use an inverter, we have to use a NAND gate. Now our gate input cost has gone up to 11. But overall, we need 2 chips. This is a 3-input NAND gate, so that's 1 chip. And then I've got 1, 2, 3, 4 2-input NAND gates. So overall, I'm using 4 out of 4 things on the NAND, the 7410, and 1 out of 3 on the 7410. Richard? No, in OR with all of its inputs inverted, bubble push this. No, it becomes a NAND. It becomes a NAND because if you've got A bar ORed with B bar ORed with C bar, that becomes A and B and C double bar with an inverter all the way over it. Right, because you got to split the line, change the sign, so you get 2 bars, but that cancels out. So overall, that's NAND. Okay, so that really is a NAND. So everything is a NAND. Okay, we actually didn't have to change the circuit at all. I just added bubbles. But our gate input cost is 11, our chip count is 2. What about the other version? The other version with decomposition, how do we convert this? Well, I can start here by placing bubbles and placing alternate bubbles there. That takes care of that. That's an OR with 2 inverted inputs. That's a NAND. Obviously, putting an inverter on the output of an AND makes it a NAND. That's okay. That's just a NAND with its inputs tied together. But that OR is going to cause us some problems. So what is an OR? Would you agree that an OR is a NOR with an inverter on the output? If I take a NOR gate and invert it, I end up back at OR. Okay, would you agree that if you bubble push a NOR, you get an AND with inverted inputs? Would you agree that this is true? A NOR gate is the same as an AND with inverted inputs. That's graphically applying to Morgan's law. A NOR B, split the line, change the sign, A bar or B bar. And. Okay, so you're on board with that. So, if you apply that all the way through, this NOR becomes an AND with inverted inputs. But that bubble still exists. That's still an inverter. I could take this bubble now and attach it to the AND. That's now a NAND. A NAND that has inverted inputs. So my technology schematic is up in the top right. That OR with inverted inputs, that's a NAND. It's perfectly reasonable to leave it in that format because anybody who's at a level of U or higher knows that an OR with inverted inputs is a NAND gate. Gates 2 and 3, those are definitely NANDs. Gate 4 has become a NAND if you invert C and D. To build this, okay, I'm going to make a slight conceit. Obviously, I've got 4 NAND gates in red and 3 inverters. So I can definitely make inverters out of NAND gates. It's one of the simplest ones to do. So for that purpose, I've got 3 inverters. So I could use one 7400 to make that happen. Or, for the sake of my sanity, I could just use an inverter chip, a 7404. So my chip count now is one 7400, which uses 4 NAND gates out of 4 NAND gates, and a 7404, which uses 3 out of 6 inverters. What is the gate input cost of that? Well, now it's gone from 9 to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Wait a minute. That other one was 11 and 2 chips. This one was 11 and 2 chips. So by all of the criteria we have specified, they're the same. The only criteria that we have not tested is the gate delay, the propagation delay. So this has a propagation delay worst path of 3. If you follow through the OR, through there, and then that inverter, that's 3 gates. This would have quite a bit longer, 1, 2, 3, 4. Well, longer. It would be a longer propagation delay time. But that was not the criteria we were given. Propagation delay was not even a consideration. So, yeah, technically one of them is better in propagation delay. What should we care about? If we're designing this, we're going to build this, right? So which one is easier to build? Well, in order to find that out, you've got to build them. You've got to go through and build both versions. So your pre-lab might involve you doing 2 different problems. So I've been taking an informal poll of the people who walk past my desk. So far, the one on the right, which is the one with the 7404, has 4 votes. The one on the left has 3 votes. No one can really give me a good, this is the best I've got. That one looks cleaner. I don't know why. So let's add to this poll. Raise your hand if you would rather build the one on the left.
That was the first one, right?
The one on the left.
Yeah.
Left. So I count 1, 2, 3, 4, 5, 6 hands. So that's plus 6. 1, 2, 3, 4, 5, 6. Raise your hand if you'd rather build the one on the right. 1, 2, 3. You guys are gonna have a problem. You're in the same group and you disagree. Yeah, hold on. Raise your hands again. 1, 2, 3, 4, 4-ish. 1, 2, 3, 4. You guys have had a bit of a discussion. Okay, you guys in my case study. What's the pros and cons?
So what I noticed about both of them, because I kind of don't want to pick either of them because there's overlap with wires on both.
There's no overlap in either case, but that's a different story.
So if you look at the power rails coming.
Yeah, that is a concession I make. If you have to cover the power, everybody knows what the power is. Everybody knows the chips have to be powered, so you can go over those and I don't care.
So then another thing I would analyze would be the orientation of the wires. The ones on the left, the blue wire in particular, that looks like it's carrying 4 input.
It is. It's a 4-input circuit.
No, I know. It's kind of tough to see. It looks like it's a bit more bent than some of the other ones on the right side where they're all even.
Yeah, okay. People see that. I think that's what Rob meant when he said it was cleaner. This one, I had to kind of sneak a wire through. I have a completely different reason for choosing. I obviously went through and I did the schematic first. I choose the right one. And the reason I choose the right one is because of these banded wires. Right here. See the black banded, or sorry, the white banded, the blue banded, and the green banded? If you look at those are coming out of the inverter. The white banded is the white inverted. The blue banded is the blue inverted. And the green banded is the green inverted. So in terms of debugging this circuit, over here I've got these 3 orange wires. I don't really know what those are. But aside from those 3 wires, just by the colors, I can tell what everything in this circuit is. That's my thought. Okay. I optimized the crap out of this. I carefully chose what chip gates went where so that everything was straight. If you guys just do this willy-nilly, you will not get something looking this nice. I purposefully didn't show you the schematic. I'll let you guys do it on your own. Technically, this one is disqualified. I went back and I reread the lab. It says specifically you have to do it only with NAND gates. Being the professor, I get to tell the book when to take it and shove it, so I did. And I built both. Anytime I say build with NAND gates, I usually mean NAND gates and inverters.
Where is the banded wire, is that part of the wire color selection?
It's right next to it. So there's a drop down, and next to it there's a checkbox. For banded wire. It says banded. You click on it. The only sort of cheap trick I pulled here, if you make a white wire banded, it still looks like a white wire. It's white wire banded with white. So I actually made this a black wire and then banded it. Just the way I could have switched the colors around, but that's what I did. But in either case, to get these screenshots, I took those red and black wires that are bridging the power rails. I moved them over so that you could see it and so forth. Every wire that has to go off to the analog discovery, I have by convention put as far left as I can. And that's just so that when I come into lab, I can plug those in and I'm done, right? If you start putting things, like you notice this pink wire. This pink wire does nothing but go from that pin all the way over to here and then off to the analog discovery. There's no reason physically that I couldn't have just gone over here and plugged it right in. The only problem is when I come back to this circuit next week or a day later in my dorm room, like I'd live in one of those hellholes. Go back here, I don't know where to plug in the analog discovery unless I've left myself some kind of a note. If I just leave that pink wire there, I know, oh yeah, that's the output. That's the only place it could go. These are conventions designed to help you out. I have not gotten through all your pre-labs yet, nor have I gotten through your exams. We will get to it. So, questions on that? How many people think they're going to have to redo their pre-lab? I have gotten to yours. I think. Yes, you have to. Okay. So, might be worth it. I have not done anything about the multisim because I don't have multisim on this machine to demo it to you. But the whole point is the order. Go back to the original order. Paperwork, which is all the writing stuff. It's up to this point here, where this is not the pen that writes on this tablet. Okay. Getting to this point and also doing this. Putting down both is perfectly legitimate. You write, I'm going to try this, and I'm going to try this. And at the end, you say, oh, I'm going to do this one, or I'm going to do that one. From there, you take this diagram, plug it right into multisim, and observe the output F. A, B, C, D go to your word generator. F goes to your logic analyzer. A, B, C, D goes to your logic analyzer. And you go back and check it with your paperwork. Where is my paperwork? There it is. You go back and you check, hey, did this connect up correctly? Does it match? If it doesn't match, then there's no point building it in fritzing because it doesn't work. Okay. Once you've done it in multisim, then you have to build the schematic again in fritzing because building the schematic will tell you what wires are left to be routed. Okay, questions on that? Okay, I think it's about time that we speak about chapter 4. Yeah, I think chapter 4 is where it's at. I'd like to talk about one thing. I'd like to talk about one more thing. If it will let me. Everybody knows what this symbol is, right? It's an inverter. What does the bubble mean? It's inverted. So, aside from the fact that these are a little bit stretched out horizontally, what would this do? Yeah, it'll add some propagation delay. It's also a buffer. It'll make sure that it always gives out a good, clean signal. So you put in a 0 here, you get out a 1. You put in a 1, you get out a 0. Here, you put in a 0, you get out a 0. Here, you put in a 1, you get out a 1. We don't talk about it because it's just a wire for our logical purposes. Technology-wise, there might be reasons to use that. We won't get to those until probably next semester with 263. And we say that we practice Boolean algebra. Boolean because there are only 2 possible values. Just for this once, we're going to talk about one other possible type of output. I'm going to draw that buffer again. It's a buffer. But off the top of this, I'm going to get one extra control signal. I'm going to call this enable. I'm going to call that A. I'm going to call that F. Now, you would be forgiven for thinking that if you put in a 0, you get out a 0. You put in a 1, you get out a 1. It's a buffer. That's its job. A buffer that looks like this is called a tri-state buffer. It's a tri-state, not Boolean anymore. And this is where things get a little bit interesting. What I said was true if the enable is 1. Okay, if you put a 1 there, you put in a 0, you get out of 0, you put in a 1, you get out of 1. If, however, you put in a 0 here, then it doesn't matter what you put on the input, you will always get something called high Z. Roughly, what is the resistance of a wire?
At the length we're using, next to nothing.
Yeah, even at lengths 10 times, 20 times, it's still next to nothing. It's roughly 0, very small. High Z is the opposite of that, very large resistances. For example, do you know what the resistance between these two fingers are? Not counting the path through my body, but this space right here. Giga-ohms or something. This isn't quite that, but figure maybe 100 mega-ohms, very large resistance. With 100 giga-ohms, or whatever we're going to call this high Z, we can effectively say that it is disconnected. It might as well be a switch that is open. No current can flow. I equals 0 in either direction. So this tri-state buffer, it's just a buffer most of the time. As long as it's enabled, it's a buffer. But as soon as you disconnect this by setting enable to be low, it doesn't matter what happens on the input. The output stops being a 0 or 1. It becomes high Z. It's neither 0 nor 1. It's floating. Floating is what inputs on a gate experience when they're not connected to anything. So if you accidentally left one of the pins of your 7400 unconnected, it would float because it has no connection to either high or low. And the weird thing about floating is the chip is going to interpret that either as a 0 or a low. It has no choice. It has to resolve to one or the other. So your chip, when you're using it, what do you think it's going to float to? Is it going to float high or float low? Low? Everybody think low? Anybody think high? See, only when I ask, do you think it's high, do you think it's okay to volunteer that it might be high? Well, the truth is, it's going to depend. It's going to depend because Murphy's Law comes into play at this point. Everybody heard of Murphy's Law? Yeah, whatever can happen will happen. Usually in a derogatory sense. Whatever shouldn't happen is going to happen right when you need to demo it to the TA. All right, so if you leave something floating, most of the time it'll probably work until you need it to work, at which point it will promptly float the other way. Murphy's Law is the bane of our existence because it just takes that little thing that, oh, it works now, and then suddenly will stop working. There's an interesting thing that you can do, though, with tri-state buffers that you can't do with any other kind of gate. If this was just buffers, what would occur on the top buffer? What voltage would be present? Right here on the output. All right, you put in a 0, you get out a 0. So you'd see 0 volts. What would appear on the bottom one? A logical one, what would be the voltage of that? Well, if we were powering it from 3.3 volts, it would be 3.3 volts. If we're powering it from 5 volts, it would be 5 volts. I'm going to choose 5 volts because it makes my math a lot easier. The resistance of a wire, we already said that the resistance of a wire is very low, practically 0. If the resistance of the wire, let's actually just establish this. What is the formula for current? I equals V over R coming from Ohm's law. Okay, so the voltage drop from this point to that point is 5 volts. R is 0. Well, we can't do a divide by 0, can we? No, dividing by 0 is a no-no. So since it's very small, let's take the limit. This is as complicated math as it's going to get. As R approaches 0, what is V over R, where V is 5 volts? What is the limit as you approach R? Well, let's just assume R is 1. What is the current if R is 1? 5 what? 5 amps. Okay, what if R is 0.1? 5 divided by 0.1 is 50 amps. No, R is 0.1, so I'm calculating I. V over R. 5 divided by 1 is 5 amps. 5 divided by 0.1 is 50 amps. As we get smaller, 0.01, 500 amps. Does anything strike you as odd about those numbers? What does this converge to? As a limit, what do we say the amperage is going to approach? Infinity amps and beyond. Infinity amps is not a thing. Infinity amps is a problem. We should avoid infinity amps at all costs. So that's why we never connect outputs together. But if I make these tri-state buffers, as long as only one of them is enabled, I can have those outputs connected together. So how could I ensure that only one of them is ever enabled? What about this? So now only one of them will ever be enabled. This is a core principle that we use in larger designs. Okay, we have to choose which item gets control over the bus. And when we're talking in chapter 4 about devices, remember this idea that with tri-state buffers, we can choose between multiple outputs and send it to a single output. Did I say output twice? Yeah. Choose between multiple inputs and send it to a single output. Richard?
In that connection of the enables, is there only one inverter in that?
There's a single inverter. So if you put a 0 here, yeah, that's going to be a 0. That'll be a 1.
Okay. So I think there's a 0 underneath. Thank you. You just drew over the 0.
Oh, yeah, no, that's from before when I said what it would be. All right, like that. Okay. All right. Now let's start talking about chapter 4. That was a little bit left over from chapter 3. Chapter 4 is, yeah, question? You'd blow up the chip. Right, so at the end of the day, you're saying that this device has to supply infinity amps. It cannot. It will keep trying to pump more and more amps out. Meanwhile, this guy is trying to accept infinity amps. Okay? The question is equivalent to what would happen if I took this and chucked it into the wall socket. The wall socket has more oomph. It's got more voltage, right? So it can push current into that, even though it doesn't want to accept it. So you'll blow up both parts. Or actually, the truth is one of them will win. The one who wins will be fine. The other one will get trodden. Okay? Like a freshman who accidentally signed up for senior design. It's just not going to end well for him. Okay? All right. Chapter 4. I need to grab a mouse for just a moment. Because I need to look at a figure somewhere. Okay. Oh, wait a minute. Oh, that's weird. Okay. Chapter 4 can be summed up as chapter 3 times n. We're just going to be doing more of chapter 3, more simplification, more K-maps. Okay. We could also say that it is multiple inputs leads to multiple outputs. Okay. Now, factoring and decomposition was kind of a side note in chapter 3. In chapter 4, it's absolutely essential. So any device that we deal with in chapter 4 is going to take on some number of inputs and have some number of outputs. Other than that, it's really just chapter 3. There are going to be common pieces inside of this that we can make use of. Okay, so maybe this piece actually goes to 2 different places and maybe it takes a few inputs there. But we're going to see that building up our design from small pieces to create a large device is going to be much simpler than trying to design the device itself, all as one monolithic unit. Okay, we're going to be dealing with many more inputs. 16, 32 inputs is not going to be unreasonable. Now, how many rows would you have if you had a 16 input truth table? 16 squared is not right. 2 to the 16, which has a number, is approximately less approximately than that. More approximate than that. The fast way to deal with powers of 2, split it into 2 digits. The tens digit tells you the prefix. The ones digit tells you the number. 2 to the 6, count it with me on your fingers, 2, 4, 8, 16, 32, 64. 2 to the 6 is 64. The tens digit tells you what the prefix is. 1 is K. So roughly 64,000 lines. Are you going to sit around and do all 64,000 lines? No. No, you're not. But if you break those 16 inputs into a bunch of smaller pieces that have 2 or 3 or 4, that you could do. All right? Okay. So there's 2 ways I can talk about this. When we're dealing with circuits that have multiple inputs or outputs, I can say either we're going to analyze a circuit that already exists, or we're going to build a circuit that has a definition, and we need to build it. How am I doing on time here? 7 minutes. Okay, we can do this in 7 minutes. I'm going to grab figure 4-2 out of the book. And actually, with the help of movie magic, look at that. Sweet. This is my circuit. It's got 3 inputs sprinkled all over the place and 2 outputs. Things I want to point out. This sub-circuit here is both its own input and then used as part of other operations. Okay? In order to solve this and decide if it works, we have to come up with a truth table for F1 and F2. Trying to do this by just analyzing the circuit monolithically and just trying to find the truth table is not going to work well. What we're instead going to do, so we're going to take this, we're going to put it off to the side. Okay. And we're going to build up pieces of the circuit. So I have A, B, C. So it's a relatively small truth table. A, B, C. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 1, 2, 1, 2, 1, 2. Nope. 0, 1, 0, 1, 0, 1, 0, 1. Whenever you are given a circuit that you need to analyze, you're going to break it up into manageable chunks. For example, in order to figure out F2, I need to figure out this whole section right here. Oh, you can't see that. This section here. That's AB or AC or BC. And they call that F2. This one is actually pretty straightforward. I can say, okay, this is F2. And it's going to be true anytime one of these three things is true. So I can look for all the places where A is 1 and B is 1. Where does that happen? In what min terms? 6 and 7. Okay. What about A and C? What min terms does that occur on? 5 and 7. So there's 5, and we've already put a 1 in 7, so it's still there. Finally, B, C. What min terms does that occur on? 3 and 7. All right, so everything else is a 0. To solve for F1, we need to know that line and that line. Well, okay, we can figure out this. This one I've labeled as T2. So I'm just going to keep appending things to this table until I have enough information. So T2 is true when A is 1 and B is 1 and C is 1. What min term is that? It's 7. And 0 everywhere else. That is 0, 0, 0, 0, 0, 0, 0. I'm going to give myself a bit of a line here to keep myself kind of neat. Okay, so now we know T2. We know F2. In order to solve for this line here, called T3, we need to know F2 bar and T1. Well, let's solve for T1. T1 is true when A is 1 or B is 1 or C is 1. Well, we know what an OR looks like. OR is only going to be false when all of the inputs are false. So that's a 0 there and a 1 everywhere else. We need to know what F2 bar is. Well, I know what F2 is, but I could write down F2 bar right there. And I'll show you why I'm going to do that in a second. So I'm just going to copy over every place I see a 0, I'm going to put a 1. Every place I see a 1, I'm going to put a 0. So there's F2 bar. To calculate T3, that is now a function of T1 and F2 bar, which we have right here. It's an AND function. So no matter how I look at this, I'm just going to be performing the AND operation on T3. One way to do this very quickly is any place there's a 0, an output is going to be 0. So those are zeros. The only time something is going to be a 1 is when both inputs are 1s, which occurs in 3 spots. So now we have T3. We need T2, which we've already made. I'm just going to go ahead and rewrite it, just so that it's right next to me. T2 is 0, 0, 0, 0, 0, 0, 0, 1. And we're ORing those two things together to get F1. So that's an OR operation. Any place I see a 1, the output is going to be 1. So looking at T2, that's the only one. Looking at T3, I've got a 1 in positions 1 and 2 and in position 4. Everything else, by definition, is 0. So that is my output for F1. So now I've solved for F1, F2. I could now decide, hey, is this circuit crap? Could it be simplified better? By just throwing it into a K-map. Throwing F2 into a K-map, 0, 0, 0, 1, 0, 1, 1, 1. Okay, 3 terms here. Looking at that, I know we're running out of time here, but I can tell you that that's AB, or AC or BC. It just so happens to be that F2 is optimized. What about F1? Build that K-map. That's 0, 1, 1, 0, 1, 0, 0, 1. You have already seen this function. This is a function you already know about. It's a basic function. First off, notice, are there any groups of 8? No. Any groups of 4? No. Any groups of 2? No. So we have 4 groups of 1, which is quite a laundry list of terms. But notice, we have a sort of symmetry here. This symmetry that appears. What does symmetry look like in Boolean algebra? Looks like some sort of exclusivity function. I don't know if this is exclusive or exclusive nor, but I could check, right, by writing down how many ones. 0 ones, 1 1, 1 1, 2 ones, a single one, 2 ones, 2 ones, 3 ones. When I look at the states that are valid here, what do I notice about the ones that I've circled? They're odd. This is the odd function. This is, in fact, A exclusive or B exclusive or C. So if you had an exclusive OR gate lying around, you could do that and reduce it a bit. All right. That's analysis. Analysis is just a really long truth table. Give yourself as much free room as you have and work your way out. I copied T2 over to here. Even though I had F2, I copied F2 bar. I made it so that it was easy to analyze, so that columns were right next to each other. When we come back on tomorrow, which is Wednesday, we'll talk about designing from a problem statement into a circuit.